In this example, we're going to find everything that we've learned to find in rational functions. We're going to find the domain, the y-intercept, x-intercepts, vertical asymptotes, and horizontal asymptotes. And also we're going to find any holes if we find some. Okay, let's start by factoring this. I'm going to start by factoring it just so that I have it ready for when I need it. So if I factor the numerator, I have a common factor of x squared times x plus 3. That's my numerator. In the denominator, I have a common factor of x squared also. And now in the denominator, I can factor this further. I have a difference of squares in the denominator that I can factor. X plus 2, x minus 2. Okay, I've factored it completely. Now that this is ready, I'm going to start by looking for the domain. Domain. It's nice to look for domain first because then you know who the party poopers are. You know who is not invited to the party. Remember that video? And you can keep an eye out for them during the rest of the process. So for domain, what we do is we take our denominator and we set it equal to 0. Now when I do that here, if I set this denominator equal to 0, I'm going to have to factor this so then I can find the zeros. I already did that work. Here it is. So let's set this denominator equal to 0, which is exactly the same value as this one, okay? So I set my denominator equal to 0, x squared, times x plus 2, times x minus 2. Now I use the zero product property that says if this product is 0, then one of these factors has to be 0, or both, or all three of them are 0. So I take each one and I equal it to 0. This is the first factor, x squared. So I say x squared is 0. And if I take square root on both sides, then x is equal to 0. That's my first factor. The second factor, x plus 2, I equal it to 0. So x has to be negative 2. And the third factor, x minus 2 equals 0, x equals 2. So when I write my domain statement, the domain is going to be all real numbers, which means any value for x, except who? X cannot be negative 2, it cannot be 0, and it cannot be 2. Why can't they be part of the domain? Because when I plug these values into my original function or into my factored function, I get a 0 in the denominator, which makes my function undefined. So these three values for x are not valid values for my function. Okay, so let's keep an eye out for these. I did my domain. Now let's go ahead and do y-intercept. For y-intercept, we set x equal to 0. And that means all these x's, I'm going to plug in a 0 and see what I get. Okay? Whatever I get when I evaluate that, that's where my y-intercept occurs. So this is like evaluating f of 0. F of 0, and I plug in a 0 anywhere there's an x. So 0 cubed plus 3 times 0 squared over 0 to the 4th power minus 4 times 0 squared. You could use this function to do this. You can use the factored one. They're all equivalent. So you can use this one. It doesn't have to be this one. This would be 0 squared times 0 plus 3 and 0 squared times 0 plus 2 times 0 minus 2. Okay, you can use either one. It's going to give you the same result. So when I evaluate this, I get 0 plus 0 in the numerator, 0 minus 0 in the denominator. And when we have 0 over 0, we call it indeterminate. Because what number multiplied by 0, the quotient, if I were going to divide this, the quotient is what number? That's the answer to this division. Well, it can be any number. So that's why we say indeterminate. Why any number? Because 0 times any number is equal to 0. Okay, so that's why it's indeterminate. So when this happens, we say that we have no y-intercept. Whenever we have an undefined function or an indeterminate function, we say that there is no y-intercept. Okay? Now let's look for our x-intercepts. X-intercept. For x-intercept, we set f of x equal to 0, which is the same thing as saying y is equal to 0. And that means this f of x here. Instead of writing f of x, I'm going to write 0 is equal to, what is this going to equal to? The numerator. We're only going to use the numerator. Okay, and we solve for x. So 0 is equal to x cubed plus 3x squared. I can write the original one. I can write the factored one. I still have to factor anyway. If I write the original one, I have to go ahead and factor that, which I had already done at the beginning, because I'm trying to solve for x. I'm trying to find x. So with the zero product property rule, I say x squared is 0, which makes x equal to 0, and x plus 3 equals 0, which makes x equal to -3. Notice for x-intercepts, this looks a lot like what I did with the domain, except that for the domain, I used the denominator. For the x-intercept, I use the numerator. Okay? So here are the possible x-intercepts. I can't say for sure they are. Now, remember I said the domain. Keep an eye out for these values. These values are not allowed in this party, and look where 0 came up. It came up as an x-intercept. It's trying to sneak in. So make sure you're always looking for this. When you look for x-intercepts, make sure nobody sneaks in. X equal to 0 is not an x-intercept, because I had said from the beginning that x equal to 0 is not part of the domain. Okay? My x-intercept, x equal to -3. When we learned how to find x-intercepts, we would take these x's and we would evaluate them in the denominator, just to make sure that I didn't get 0 in the denominator with the x value. But since I found my domain as my first thing here, I already know which x's create trouble for me in the denominator. These 3 x's are the 3 x's that will cause problems down here. So I don't really need to take -3 and plug it into the denominator, because I've already found out with the domain which numbers I cannot have, because these are the only ones that will give me 0 in the denominator. So I can just go ahead and say that my x-intercept is at -3. If you still want to go and check, you can go ahead and do it, but it's not necessary. We already know the values I cannot have as x-intercepts. Okay? So I can say my x-intercept is -3, 0. And you found your x-intercept. So far, I have no y-intercept. I have one x-intercept at -3, 0, and I have this domain. Okay? So see how helpful it is to find the domain first, and then it saves you a little bit of work. Next thing I'm going to find is my vertical asymptotes, possible vertical asymptotes. And remember, when we look for possible vertical asymptotes, we work with the denominator, which we already did here. It's basically repeating the same thing we did here. We take the denominator and we equal it to 0. 0 is equal to x squared, and I'm going to use the factored form because I'm not going to go through that work again. Okay, and I solve for my x's. So x squared is equal to 0. That means x equals 0. X plus 2 is equal to 0. X equals -2. And x minus 2 is equal to 0. X equals 2. Okay, these are possible vertical asymptotes. Now let's check. I take the first one, x equal to 0. I already know x equal to 0 is not part of the domain. I know x equal to 0 is going to make my function undefined. That's why it might be a vertical asymptote, okay? Because this one and this one and this one, all of these are not in the domain. So what role do they play in my function? Well, they can be holes or they can be vertical asymptotes, and that's what I want to find out. So for x equals 0, how do I know if it's a vertical asymptote or a hole? Well, I take the 0 and I plug it into the numerator. If I do not get a 0, it's a vertical asymptote. If I do get a 0, then I have to compare multiplicities. So let's do that. In the numerator, x equals 0 comes from this factor, x squared equals 0. So this is the factor in question, x squared. And notice this factor I have as a common factor in the numerator and in the denominator. Notice their multiplicities. The multiplicity of this x in the numerator is 2, and in the denominator it's also 2. So when the multiplicities are greater than or equal, the multiplicity in the numerator is greater than or equal to the multiplicity in the denominator, that means I have a hole. So this here is a hole. This is a hole. Okay? Just because the multiplicities are equal. And notice I need to use the factored form to evaluate this because that's where I see my factors very clearly. Here I don't see my factors, okay? Now let's take the next one, x equal negative 2. X equal negative 2, if I plug it into the numerator, I get 4 and 1, and 4 times 1 is 4. I do not get 0, so automatically this is a vertical asymptote. For x equal to 2, plug it into the numerator. I get 2 squared 4, and 2 plus 3 is 5. That gives you 20. I did not get a 0. Automatically, this is a vertical asymptote. So notice that the party poopers here now have a role in my function. I know they make my function undefined. I want to know what kind of undefinedness, if the word exists, they play in this function. So now I'm saying, well, you're a hole, you're a vertical asymptote, and you're a vertical asymptote. Okay, that's what we did here. We defined what role these play in my function, and here it is. For vertical asymptotes, I can go ahead and straight away say I have two vertical asymptotes at x equal negative 2 and at x equal 2. And for my hole, I need to find that hole more precisely. Okay, so let's continue up here. When I have a hole, remember this x equals 0 just tells me my x coordinate of the hole. I need to find the y coordinate of that hole. To do that, I have to plug in this hole into that function. So I have to say f of 0. But I'm going to use the factored function simplified form. Simplified means I cancel out the common term. So in this case, I would cancel out this term and this term. And here's the function that I'm going to use to plug in the 0. X plus 3 over x plus 2, x minus 2. And when you plug in 0 for x, in the numerator you get 3. In the denominator you get 2 times negative 2, which is negative 4. That means this is negative 3 over 4. And that is my y coordinate for my hole. Okay? And there you found your hole. So let's move this down a little bit. And let's clearly state that I have vertical asymptotes at x equal negative 2 and x equal 2. That's my answer for vertical asymptotes. And I also have a hole. Where? At 0, negative 3/4. And this is coming together very nicely. Okay? I'm done with my vertical asymptotes. Let's do horizontal asymptote, which is the last thing I'm going to look for. Now here's the rule for horizontal asymptote. I look at the leading terms in my original function, x cubed, x to the 4th power, and I compare the degrees. If the degree in the numerator is less than the degree in the denominator, in this case it is. For horizontal asymptotes, I'm going to look at this. Let me rewrite the function here. X cubed plus 3x squared over, let me move this down, x to the 4th power minus 4x squared. Okay. When I look for horizontal asymptotes, I look at the leading terms only. But make sure, be careful, make sure that these polynomials are written in standard form so that you can identify what the degree is. Okay, and now I compare the degree. This is a degree 3, this is a degree 4. When the degree in the numerator is less than the degree in the denominator, my horizontal asymptote is y equals 0. That's where it's at. So in this case, the degree is less in the numerator than in the denominator. I have a horizontal asymptote at y equals 0. And that would be my answer for horizontal asymptote. If they were equal degrees, then my horizontal asymptote would be at the coefficient over the coefficient. We'll see that in the next example. And if the degree is greater than the one in the denominator, then there's no horizontal asymptote. Those are the 3 cases. So here we have the first case where the degree is less in the numerator than it is in the denominator. Okay? You only look at the leading terms, meaning the terms with the highest exponent. Okay, so we have everything we need for this function. When we start sketching, this is more or less what we're going to have. We're going to have our x and y axis. Here you have it, x and y, and you would take your, there's no y-intercept, so I don't have any intercepts here. I have an x-intercept at -3, 0. Let's say this is -3. That means I have, my graph is going to somehow cross this x-axis at -3. I have a vertical asymptote at -2. That means I have an imaginary vertical line at x equal -2. And I also have a vertical imaginary line at x equal 2. These are my guide lines for when I sketch the graph. I have a hole at 0, -3/4. 0, -3/4. Let's say this is 1. 3/4 is about here. So I'll have a hole here, an open circle. And I have a horizontal asymptote at y equals 0, which is my x-axis. That's my horizontal asymptote. We need to learn one more thing to do before we start sketching, okay? And we'll do that later on. For now, just worry about knowing how to find the domain, the y-intercepts, the x-intercepts, vertical asymptotes, any holes, and horizontal asymptotes. I hope this video helps. Go over it again. Try it on your own after you watch it for the first time. And then, keep looking at it till you're able to get it. I will see you in the next video with one more example on finding everything, okay? I'll see you in the next video.